Hello everyone, and welcome to the M2L31 series Level 1 training course. In this video, we're going to walk through a low power UART sample program. We'll demonstrate how, in low power mode, you can use auto operation mode to let the hardware automatically handle low power UART data transmission without requiring continuous involvement from the CPU. This approach is especially useful for low power applications, where you want to keep the system efficient while still maintaining reliable communication. You can download the example program from the link in the video description below. Once you've downloaded it, just extract the files and open the project in the Kyle development environment following the provided path. In this sample program, we're using the NuMicro M2L31 SG development board, specifically the virtual COM port on the right side of the board, or VCOM, to output strings to a terminal on the PC. So, just like you can see in the diagram, make sure to switch the TXD toggle to the right. This allows the board to send data out through the virtual COM port correctly. For this demo, PB13 is configured as the low power UART transmitter pin, and all transmitted messages will go out through this pin to the terminal. Let's start by walking through the overall flow of this sample program. First, we use a low power timer to generate a trigger every 500 milliseconds. Each time this trigger occurs, it activates low power PDMA channel 0. Once PDMA is triggered, it automatically transfers data that was previously stored in low power SRAM to the low power UART. As a result, the string data is sent out and displayed on the terminal, without requiring the CPU to actively handle the transmission. At the same time, we also configure the system so that when the PDMA transfer is completed, an interrupt is generated to wake up the CPU once. After that, the system immediately returns to low power mode. In this way, most of the data transmission is handled entirely by hardware, allowing the system to maintain very low power consumption. Next, let's take a look at the relationship between each peripheral from the bus matrix point of view. In this architecture, the CPU acts as a master, so it can read from and write to peripherals inside the low power domain. At the same time, within the low power domain, the low power PDMA also plays the role of a master. This means low power PDMA can directly read data from low power SRAM and then write that data into the low power UART, completing the data transmission by hardware. Next, let's move on to the program overview. If you look at the main function, you can clearly see the overall structure of this example. In this low power UART demo, the key modules we use are the low power timer, low power UART, and low power PDMA. These three blocks work together to handle the data transmission automatically, without requiring the CPU to stay active. As for the basic system initialization, such as the minimum current initial function, system initial function, and UART initial function, those steps are the same as what we explained earlier in the low power timer example video. So here, we won't repeat the details, and you can refer back to that video if you want a deeper explanation. First, let's start with the low power timer configuration. Here, we set the timer to run in periodic mode, so it counts once every 500 milliseconds. Each time the timer reaches the end of its count, it automatically generates a trigger. This trigger is used to start the low power UART data transmission, so the data can be sent out regularly without needing the CPU to step in. In other words, the timer acts as the heartbeat of the system, driving UART transfers at fixed intervals while keeping the system in a low power state. Next, let's move on to the low power PDMA configuration. In this example, we configure low power PDMA to operate in scatter-gather mode. That means we define all the low power UART transfer tasks in advance using a descriptor table. Once everything is set up, the hardware can automatically follow these descriptors and handle the data transfers without any help from the CPU. When low power PDMA finishes all the scheduled transfers, it will generate an interrupt. This interrupt is used to wake up the CPU, allowing the software to continue processing before the system goes back into low power mode again. Let's take a closer look at how the scatter-gather descriptor table is configured. In this setup, each transfer uses an 8-bit data width, and we send 6 data items at a time. The source of the data is a source array stored in low power SRAM, and the destination is the low power UART data register. So in other words, once the transfer is triggered, the hardware will automatically move the data from low power SRAM directly into the low power UART data register, 1 byte at a time. This is how the string data is sent out through low power UART without requiring the CPU to be involved during the transfer. Next, we move on to setting up the low power UART transmitter. Here, we first configure the transmitter pin for low power UART and then set the baud rate so the output data can be sent correctly to the terminal. At the same time, don't forget to enable the setting that allows low power PDMA to access low power UART. Otherwise, the hardware won't be able to move data automatically. Finally, we define the trigger condition for the PDMA transfer. In this example, we use low power timer 0 as the trigger source. Every time the timer finishes counting, it will automatically trigger PDMA, and the data transfer will start without any CPU intervention. Finally, let's take a look at how the program actually runs. After all the initialization and setup is complete, the program prepares 48 pieces of data stored in the low power SRAM source array and then enters NPD3 mode. At this point, the low power UART auto operation mode is active. Inside the loop, low power PDMA continuously transfers the data, and under certain conditions, it wakes up the CPU. So what are these 48 pieces of data? As you can see here, they are filled sequentially in alphabetical order, A, B, C, and so on, into the array. Next, we will program the board and see the demo in action. Now, you can open the Kyle project file from the path we mentioned earlier. Next, click Build to compile the project. Once the compilation is complete, connect the board to your computer using the programmer and debugger USB. Then, click Download to flash the program onto the board. After the program is successfully loaded, open your serial communication tool. Remember to turn on the TX switch on the board as we mentioned earlier, so you can view the data transmitted from the low power UART. Next, let's use the current measurement software to actually check how much current the system is consuming. From the results, we can see that since we don't need to keep waking up the CPU in this application, the overall average current consumption is only around 20 microamps. Following the program flow, we can actually see the system's behavior directly when measuring the current. The current peaks correspond to the CPU being woken up once after the low-power PDMA finishes transferring all 48 data points, and then it goes back into power down mode. You can try changing the length of the data transfer to see how it affects the low-power behavior. That wraps up our example program demonstration for the low-power timer UART in transmit mode. If you want to see an example for receive mode in low-power operation, please check the link in the info section to download the related sample code. Thanks for watching, and feel free to contact us if you'd like to learn more.